Hello, Assalamu alaikum. How are you all?
Walaikum assalam. Fine.
Okay, please tell me your names. Have you all joined by your actual names?
Yes.
Okay, so we have Zoya, Ayla, Shafe, and Ahmed. Right? Am I right?
Yes.
Yes.
All right, great. So this is going to be our first session. I'm going to share the screen with you. Let me know if the PDF is visible. This session is basically, and all the sessions till by now, by the end of, inshallah, by the mid of March, we will be completing and going over through the IGCSE chemistry syllabus. Okay. And throughout the syllabus, I'll be giving you a gist basically of the complete syllabus. And up till now, I am basically hoping and I'm presuming that you guys have already gone through the syllabus. Have you?
Yes.
All right.
Yes.
Okay. So let's start off with the first topic. The first chapter. This is basically your particulate nature of matter, or you can also say the states of matter. Here we're going to look into the kinetic theory of matter, the changes of state, the heating and the cooling curves, and diffusion. Okay. Diffusion and the Brownian motion, basically. Okay. So let's start off when we say that. When we talk about matter, we say that matter is basically any substance or anything which basically is occupying certain physical space. Okay. So it has to occupy the its physical space, and it is going to be a certain, and then you're going to basically divide it in three different states of matter, and that is, you already know, it's solids, liquids, and gases, right? Now, the kinetic particle theory of matter basically tells you, if you decode this terminology, and you say that in literal meaning, kinetic basically refers to movement, or it refers to something which is moving around. Okay. So this theory of matter basically is about these tiny particles, or whatever matter you're talking about. It is always in its constant motion. So kinetic particle theory, or kinetic theory of matter, states that matter, which is made up of any tiny particles, that is, could be atoms, could be molecules, they are always in a constant random motion. Is this point clear so far?
Yes.
Okay.
Yes.
Then, when we look into this, their characteristic properties of solids, of liquids, and of gases. So, solids, they have a fixed volume and they have a fixed shape. Similarly, when a certain thing has a fixed volume and has a fixed shape, you can also think of that their arrangement would be a very regular arrangement. For instance, if you look into this, is everyone able to look into uh, the table here?
Yes.
Yes.
Okay, so this table basically signifies that the solids, their particles, they are in a regular pattern, they are very well organized, and they are only able to vibrate around their fixed positions. Okay, and certainly if you provide them with energy, they're going to absorb that energy. Specifically, we're talking about thermal or heat energy. So they're going to absorb that heat energy, and then they're going to convert their state or change their state of matter. However, um, the particles in a solid, they have very least amount of energy, or they have very low energy, which is why their movement of the particles is that they're only able to vibrate around their fixed positions. Okay. So all of these characteristics, they are basically interconnected with each other. Hence, they will be helping you out to figure out what the state of matter is. For instance, if I say that there is a certain state of matter and you have to identify that state of matter. It is the particles, they're very regularly arranged. They can only vibrate around their fixed positions, and they have very low energies, and they have a fixed shape, a fixed volume, and they're higher in densities. This means that we're talking about solid, right? When I provide a solid, supposedly I have a substance and this is a solid substance, and I provide it or I give it some heat amount, some amount of heat energy. Okay. This heat energy will be absorbed by these particles, these solid particles. As a result, this is going to change its physical state. Okay. And it is going to convert into its liquid state. This is basically interconnected with the basic idea of that the particles in a solid, they gain heat energy. Okay, these solid particles, they're going to gain heat energy. As a result of this heat energy, can someone tell me, you must have also gone through physics and everything. So this heat energy, can this be converted, or will this be damaged or destroyed? Is
It
it
can be
going to?
converted.
Yes, it is going to convert. Okay. And this heat energy will be converted into the kinetic energy of these particles. Okay. It will be converted into the kinetic energy of these particles. So as a result, these molecules, these particles which are present in this state of matter, they're going to absorb that heat energy and will convert all of that heat energy into kinetic energy of themselves. Okay. So they're going to possess that kinetic energy. And as a result, this energy in liquid particles is greater than the energies in a solid. Okay. Hence, they are able to move around each other. They are able to randomly go past each other. Also, their arrangement will be distorted, will not be regularly arrangement as it was in a solid. Okay. So their arrangement is going to become a random arrangement. Their density is going to decrease as compared to in a solid. They will be moving around each other, and their energies of obviously also increase. Is this point clear so far?
Yes.
Do we
Yes.
have any questions till now?
No.
All right, great. So then what happens furthermore? Now, when this substance is now a liquid, okay, so this will again gain so much heat energy. The supposingly I'm not stopping, I'm not completely stopping the flame. So what is going to happen to this liquid particle? It is going to gain further heat energy. As a result, it is going to convert into gaseous state. And that is again because of further gaining of heat energy, which will be converted into kinetic energy of the particles. As a result, they will be moving randomly and very quickly along in all directions. Okay. And they will have the highest energy. As a result, their density is also going to decrease. They will have a random arrangement. Gases, they do not have a fixed volume. Like liquids, they usually take the container's shape. Okay. They have very less density. Okay. And they will be all randomly moving around in all directions. Okay. Also, the gaseous particles, they if supposingly they're in a container and it is a closed container, so these gaseous particles also, since they are randomly moving around in all directions, they will be colliding with the particle and the other particles and the walls of the container. As a result, the pressure within the gaseous container also increases. Okay. So these are two different concepts which are all interrelated with each other. They're all interconnected with each other. And you have to grasp a bit of every concept so you're able to link all of the concepts. So usually what the questions, they are usually like in your exam paper, they are going to be dependent on, you will be asked to define the changes of state of matter, um, with respect to or in terms of the particle collision theory and or the kinetic particle theory. Okay. So you will be asked that this kinetic particle theory will be asked in this dimension. Okay. So up till now, do we have any questions?
No.
Easy, all clear? Okay. There's one more terminology that you should know. That is intermolecular forces of attraction. Intermolecular forces of attraction is basically um, your these particles. They are connected with each other because of these forces of attraction. Okay. So these forces of attraction, if they are overcome, okay, and if they are broken, okay, they are get or these intermolecular forces of attraction, they get weak. Okay, so what happens? The change of state will take place. How? Because the structure of the state of matter will completely change. Why? Because if you look into this, supposingly this is a solid. Okay, solids are regularly arranged. They have strong intermolecular forces of attraction. Why do they have strong intermolecular forces of attraction? Because they are so compactly arranged. As a result, their intermolecular force of attraction is very, very strong, keeping them in a fixed shape, right? Now, when you provide heat energy or the thermal energy, that allows them to absorb that heat energy, hence overcoming this intermolecular forces of attraction, hence weakening these forces of attraction, and as a result that they are going to gain that kinetic energy and they will start to move apart. When they start to move apart, basically their forces of attraction get weak and the change of state as a result takes place. Okay. Further moving on, you should have a bit concept of evaporation and boiling. What is evaporation? What is boiling? Yes, anybody?
Evaporation happens at the surface of the liquid while boiling happens throughout the whole liquid.
Yes, very good. And anything else? Any further point anybody wants to add in?
Boiling happens at a specific point, and evaporation happens after the boiling point.
After the boiling point or before the boiling point?
After.
No, it basically takes place before the boiling point. When solids, they convert into a good, both of you, good, Ayla and Zoya. So for instance, if you look into these three beakers, okay, there is the first one has ice, the second one has water, and the last one basically shows or depicts boiling, which is takes place. And how all of them, they are different with each other is, in the first state you are able to notice that ice is changing into water, that is solid is converting into liquid. What is this process called? This process is referred to as melting.
Melting.
Yes, very good. So when solid converts into liquid, that is referred to as melting. Okay. So melting only takes place at a certain temperature. It cannot take place at any other temperature. And that melting point is going to be a sharp melting point if this substance is going to be a pure substance. So for instance, if you look into this beaker only has ice. It does not have any other substance or any other impurity added to it. Okay. So when no impurity is added to this ice, this means it is pure ice. This pure ice will only have one certain sharp melting point, and that will be 0 degrees Celsius. Ice is going to melt to convert into liquid water, and this process, this phase is referred to as melting. After which, when you're going to heat up the water, the temperature is eventually going to rise. When the temperature is rising, the water molecules, they are gaining heat energy. They are gaining heat energy and they're converting that heat energy into kinetic energy. When they're converting that heat energy into kinetic energy, they're basically trying to overcome their intermolecular forces of attraction. When they're overcoming their intermolecular forces of attraction, some of the water vapor, some of the water molecules basically at the surface only, the ones which are present at the surface, they are going to gain enough heat energy. They are going to gain enough heat energy that is going to cause them to overcome their intermolecular forces of attraction in liquid molecules. As a result, they start to evaporate, or also we can say they vaporize. Okay. So this process is referred to as evaporation. And evaporation always takes place less than the boiling point. Okay. It is always any temperature but less than the boiling point of that particular substance. Okay. So the only the surface molecules, they start to evaporate, not the rest of the molecules. Okay, since they don't have gained, they haven't gained sufficient heat energy or sufficient kinetic energy, basically to overcome their intermolecular forces of attraction. Hence, they are not going to vaporize. Is this point clear so far?
Yes.
Yes.
So any temperature, like even if it's 80, even if it's 85, even if I say it's 90, 95, 96, okay, degrees Celsius. So at any of this temperature, but it must be less than the boiling point, that you are going to refer it to as evaporation or vaporization, which is taking place. Okay, it is not referred to as boiling. As soon as you see that throughout the liquid, all of the water molecules, they have gained sufficient energy, they've all overcome their intermolecular forces of attraction, they will quickly change their state from liquid to gas and will be seen as steam, as gaseous vapors. Okay, and at that point in time, the temperature which should be the boiling point of that particular substance of water, okay, which is 100 degrees Celsius. So as soon as that boiling point is reached, the liquid molecules, they convert into gaseous vapors, okay, and it is going to be a sharp boiling point if this substance is a pure substance. Okay, why am I emphasizing on this purity and impurity? Because I will give you another concept afterwards. Okay, is this point clear so far?
Yes.
Okay, so up till now we have basically gone through that solids, they convert into liquids and they convert into then gases. But this can also take place vice versa, right? Gases, they can also convert into liquid. What is this referred to as? The process is
Condensation.
condensation, and liquids converting into solids is
Freezing.
freezing. Very good. And if solids convert into gaseous state without the liquid phase in between, no liquid phase in between.
Sublimation.
Sublimation, excellent. And if gases convert into solid without this liquid phase in between, that is desublimation or deposition. Okay. So, and certain examples of this sublimation or desublimation would be that you must have seen iodine, solid iodine crystals. They convert completely into gaseous iodine vapors. Solid iodine converts completely into gaseous iodine vapors. Okay, this is one example of sublimation. Any other example? Vice versa would be desublimation or deposition. Do we have any other examples?
Dry ice.
Dry ice, very good. What is dry ice? It is solid carbon dioxide. Okay, so solid carbon dioxide completely converting into gaseous carbon dioxide without any liquid phase in between is referred to as sublimation. Okay. Similarly, camphor balls. Okay, they're white colored balls, so that is also camphor. It converts into gaseous vapors without any liquid phase in between. Okay, so these are certain examples of sublimation. Moving on, let's go through a bit of the theory, and then we're going to look into the heating curves and the cooling curves. When substances they are heated, the particles they absorb thermal energy, and then it is converted into the kinetic energy, which is basically the basis of the kinetic theory of matter. Heating a solid causes its particles to vibrate more, and as the temperature increases, they vibrate so much that the solid starts to expand until the structure breaks and the solid starts to melt. Okay. So all of these phases, they have to take place for this change of state to take place. Okay. For this change of state to occur. Upon further heating, the liquid substance is going to expand furthermore, and some of the particles are going to gain sufficient energy to overcome their intermolecular forces of attraction. As a result, they evaporate. When the boiling point temperature is reached, all of the particles they gain enough energy to escape, and the liquid starts to boil. So all of these changes in state, they are represented graphically, and that is referred to as a heating curve from solid to liquid to gas, and vice versa would be the cooling curve. These curves, they represent or they show how the changes of state basically take place with the passage of time as the temperature increases. Okay, so if you look into this one for the first curve basically indicates that at first, the substance is a solid. The temperature starts to rise. Okay. As soon as this a certain temperature is reached, it starts to melt. Okay. And you see a plateau phase or a horizontal line throughout this time period. Okay. The temperature, this means stays a constant at this point. All right. So this temperature is referred to as the melting point of this solid, okay? The first straight horizontal line. Then as soon as it has completely converted into a liquid substance, the temperature again starts to rise in. In this oblique line, it is completely a liquid, okay? And then another certain temperature, which is referred to as the boiling point, it is reached. And at this boiling point, the temperature stays a constant. Is this point clear so far?
Yes.
Then again, when this vaporization takes place, okay, when completely all the liquid molecules they have vaporized, they have converted into gaseous state, the temperature starts to rise in again, right? Now tell me what is happening in this plateau phases.
The liquid is vaporizing.
The liquid is vaporizing. Okay, for the second one, we know that these state changes they are taking place, but you are providing in heat energy, right? So why is the temperature not increasing? Why is this a constant horizontal line, a plateau phase?
Yes, it's because the liquid will be like absorbing the heat energy in order to change into gas, so the temperature remains constant.
Yes, very good. So basically, all of the heat energy which you are providing in, this doesn't mean that you have switched off the flame. No, you are providing in heat energy to that substance, but it is not it is basically absorbing that heat energy or utilizing that heat energy to convert its state of matter. Okay, so which is why as a result the temperature stays constant. Okay, so as a result, the temperature stays a constant. So, which is why you see for the first one, for the first plateau phase or the horizontal line, you see that melting takes place, and for the second one, vaporization takes place, where liquid is converting into gas. Okay, at this point in time, let me just use a different color for this one. So at this point in time, here and here, at this point, all the solid particles, they have completely converted into liquid. And at this point, all the particles, they have been completely converted into gas. Okay. But over here, there will be certain molecules, there will be certain particles which are going to be solid, or they're going to be liquid. And for the second phase, they are going to be gas, or they're going to be liquid. Is there any question regarding this particular curve?
No.
Everybody's clear regarding this?
Yes.
Okay,
Yes.
all right. So moving on furthermore, then we have the vice versa will be referred to as the cooling curve, okay, where gas converts into liquid, and the first plateau phase will be condensation, and the second plateau phase will be referred to as freezing, and then this is basically going to go from top to bottom where when the temperature is decreasing, okay. Moving on furthermore. Okay, so now let's go through certain questions usually which come up in your paper, specifically in paper 2 and paper 4. They refer to sharp melting point and sharp boiling point. Okay. Or you are sometimes asked that a substance is given to you and you have to tell whether this substance is going to be a pure substance or an impure substance. So, purity or impurity of any substance can be determined by its melting point or boiling point. Purity or impurity of any substance can be determined by melting point or boiling point of that substance. Okay. So, how you going to identify that one particular substance is a pure substance or it is an impure substance? If a substance has a sharp melting point, what do I mean by sharp melting point? It means a fixed melting point. For example, water has a fixed melting point, ice has a fixed melting point of 0 degrees Celsius, water has a fixed boiling point of 100 degrees Celsius. Okay. So fixed melting points and boiling points, or sharp melting points and boiling points, basically mean that they do not have any impurity added to it. If a substance is impure substance, how is it going to affect its melting and boiling point?
It will have a range of melting and boiling points.
Yes, it will have a range of melting and boiling points, or specifically, the melting points will usually decrease and the boiling points usually increase when an impurity is added to it. Okay. So any substance which will have any added impurity in it will cause its melting point to decrease and will increase the boiling point. Okay. So if you are given either a range of temperatures or in any of the options which is given to you, this means that your reflexes should tell you that particular this substance, whatever which is mentioned in the context of the question, is basically an impure substance, which is why it has disrupted its melting and boiling point. Is this clear so far?
Yes.
Yes.
All right. Let's move on furthermore. And now we have the effects of temperature and pressure on the volume of the gas, which we are going to discuss. For instance, there is a balloon you see in the diagram, which is being heated up. Okay. As a result, we see that the balloon expands, right? And as this balloon is So when you see that the balloon is being heated up, it starts to expand. Okay, and as soon as the temperature is cooled down, the balloon is going to constrict, or it's going to its volume is going to decrease as a result. Okay, so can someone tell me how the temperature, because of these the results or these reductions, how are you able to tell that how temperature affects the volume of the gas? Can we develop a relationship between them? The
Yes.
temperature, yeah, how?
When temperature is increasing, the volume increases because the balloon becomes bigger.
Hmm.
And when
This
the
means,
temperature
yeah, continue.
and when the temperature decreases, the volume decreases because the balloon gets smaller.
Yes, good. So basically, and can you correlate this with the kinetic particle theory?
When temperature decreases, the particles they lose kinetic energy, so they move
Hmm.
less, they collide less, and then the balloon shrinks.
Yes, very good. And similarly, vice versa. Yes, that's right. So this basically means that both of them, they have a directly proportional relationship, right? What's your name?
Ahmed,
Ahmed. Okay, good, Ahmed. So, as Ahmed said, that when the temperature increases, the volume also increases for a gas. And similarly, if you're going to decrease the temperature, the volume also is going to decrease. So, this question can also be asked by the examiner in this particular dimension, where you will be asked to determine the relationship between the two. Okay, so you this is one dimension in which this can be asked, and the examiner can also ask you to describe this furthermore and explain it using the kinetic particle theory. So you will have to implement that theory. You will be explaining that as you're increasing the temperature, the heat energy is increasing. And as a result, that increased heat energy is basically being converted into the kinetic energy of the gaseous molecules or the particles. As a result of gaining kinetic energy, the gaseous particles, they are going to be moving around randomly in all directions, and they will be hitting the walls of the container. When they hit the walls of the container, since this balloon is basically a flexible container, right? So the it is going to expand, it is going to stretch. Okay, as a result, the volume is going to increase. Okay, similarly, if we look into the pressure and the volume changes. So pressure and volume changes, they are inversely proportional to each other. For instance, if you increase, supposingly, if you look into this diagram right here, there are gaseous particles which are present within a certain container, and there is a plunger. When you push in the plunger, you're basically increasing the pressure, right? When you increase the pressure, the volume decreases. The gas particles, they're going to be compressed within a smaller volume, right? This means that increasing the pressure decreases the volume, which shows an indirectly proportional relationship between the two, right? Is this point clear so far?
yes.
Okay, great. So then again, we have one more. Supposingly, if I say that you have a certain container and it is a closed container, okay, and there are gaseous particles which are present within it, and you increase the temperature of the gaseous particles so that they start to hit the walls of the container, and they start to collide with each other as well. Okay, is it going to affect the pressure of the gaseous particles?
Yes,
How?
the pressure will decrease
Why will the pressure decrease?
because the volume of the because the volume of the balloon will increase because they are hitting each other more. And
नहीं नहीं अभी हम Ayla, listen. We're right now talking about the closed container. Okay. So in a closed container, when you are increasing the temperature. I said when the temperature increases, the kinetic energy of the gaseous particles increases. ठीक है? जब kinetic energy increase होगी particles की, तो what is going to happen?
The pressure is gonna increase.
The pressure is going to increase. ठीक है? The pressure is going to increase. अब आपने सही बोला है. ठीक है? So earlier you were saying pressure is going to decrease. You were saying vice versa. तो अब आपने सही बिल्कुल बोला है कि जब when the gaseous particles they gain kinetic energy, as a result they in a closed system their pressure is going to increase, okay, when they are going to collide with each other and also with the walls of the container. Now this is clear. This point is clear so far.
Yes.
Yes.
All right, great. Then moving on furthermore, so an increase in temperature increases the kinetic energy of the particles as the heat energy is transformed into the kinetic energy, so that they move faster. As the temperature increases, the particles in the gas they move faster, impacting the walls of the container more frequently. If the container walls they are flexible and stretchy, just like in balloon, the container gets bigger and bigger, so it starts to expand. Also in a hotter air balloon. So if the container is made smaller, supposedly, this means that then the gaseous particles they are going to hit the walls of the container more frequently. This means you're increasing the pressure. Making the container smaller means you are increasing the pressure. When you increase the pressure, the gas particles they hit the wall more frequently. Hence, furthermore, enhancing that gaseous pressure. Okay. As a result, the volume of the gas is going to decrease. Is this point clear so far? Yes. Are we clear?
Yes.
Yes.
Okay. Okay, next up we have Brownian motion. So scientist, he basically named Brownian. He observed under a microscope that a pollen grain was suspended in water, where that pollen grain was randomly moving around constantly in random directions. Okay. And he proposed this theory by just looking at this pollen grain, that the water molecules they were actually bombarding that pollen grain in the causing it to move in random directions. Okay, having its erratic random movement. Okay. So as a result, he proposed this Brownian motion theory, which is basically defined as the erratic random motion of the particles in a fluid, which is caused by the continuous bombardment from the water molecules here in this case scenario. Okay. So for instance, if you see that smoke particles or any other particles, they are randomly moving around, they are basically moving around in different directions because of the air molecules which are actually constantly bombarding them. Okay. Next, we have diffusion. Diffusion is basically the net movement of the particles from a region of higher concentration to a region of lower concentration. This means that when we're going from higher concentration to lower concentration, this means that we are going down the concentration gradient. Okay. And always the particles, they basically move from higher concentration to wherever they are in low concentration. So this random movement of the particles basically allows this diffusion to take place. And if this is only solely referred to in the water molecules, then it is referred to as osmosis. Okay, but it is not part of the syllabus. Okay. Diffusion is on can be affected by, or the rate of diffusion can be affected by two different things. Either the temperature is going to affect it, or molecular mass is going to affect it. Okay, so the rate of diffusion is basically that a particular substance, how long does it take for a particular substance to travel from higher concentration to a low concentration, or how long does it take for them to diffuse. Okay, so if I increase the temperature, do you think that the diffusion is going to increase, the rate of diffusion is going to increase, or is it going to decrease?
Increase.
Increase. Why?
Because they have more kinetic energy, so they move faster.
Yes, very good. So basically, when you increase the temperature, they gain kinetic energy. As a result, their rate of diffusion also increases. This means that they move very quickly, very fast from a region of higher concentration to region of lower concentration. Similarly, vice versa, when you decrease the temperature, their rate of diffusion will slow down. They will slowly move from higher concentration to lower concentration. Similarly, the next factor which can impact the rate of diffusion is the molecular mass. When you increase the molecular mass of or certain substance which has greater molecular mass is basically heavier in weight, will take more time to diffuse from a region of higher concentration to a region of lower concentration. Okay. And similarly, if anything which has less relative molecular mass or is light in weight will have faster rate of diffusion. Okay, so rate of diffusion and molecular mass, they are inversely proportional to each other. Okay, and rate and temperature, they both are directly proportional to each other. Clear? If one is going to increase, the other is also going to increase. And if molecular mass increases, the rate is going to slow down. And if the molecular mass decreases, the rate of diffusion is going to be fast. Is this point clear?
Yes.
Okay.
Miss, are these the only two
Yes.
factors?
Sorry?
Are
Sorry,
these, are these the only two factors?
are these? Yes, yes. These are the two factors.
Okay.
Yeah. And then, okay. So lastly, we basically have, you can say, a representation of how this takes place. So if this is a closed tube, you see here, this is a closed tube. At both ends, you have a stopper or a bung which is inserted on both the sides, and there are two cotton wools which are concentrated hydrochloric acid, and one is dipped in concentrated ammonia solution. Now, ammonia, since it has a relative molecular mass of 17, and hydrochloric acid having a relative molecular mass of 36.5, okay, we will discuss this in the next session, how we are able to find out the relative molecular masses. But for now, the MR, or the relative molecular mass of the two, are given to you, supposing. So which one is light in weight, ammonia or hydrochloric acid?
Ammonia.
Ammonia is light in weight. Okay, so this means that ammonia's rate of diffusion is going to be, the MR is less. This means the rate of diffusion is going to be fast. It is going to travel very quickly. It is going to travel quickly. As a result, it will be able to travel further away from its original position. Okay, hence you see that after it travels this position from its original position, it is able to react with the hydrochloric acid. Hydrogen chloride then diffuses, also diffuses at the same point. But since its relative molecular mass is greater, this means that the rate of diffusion is less. It has less rate of diffusion. It is going to slowly diffuse. When both of them, they react with each other, they create this white ring of ammonium chloride, NH4Cl, which is produced here as a result. Okay. Is this point clear so far?
Yes.
Okay.
Yes.
Also, there could be various other ways in which you can the examiner can ask you questions related to this. So this concept should be very crystal clear. Okay, and supposingly, if you look into this diagram, you see that there is only very less difference which is traveled by hydrogen chloride. This means that hydrogen chloride is having slow rate of diffusion, which would make you think that it is a heavier molecule. Okay. Similarly, likewise, the ammonia gas is able to travel a very long distance from its original position. This basically means that it is having a greater rate of diffusion, which means that its relative molecular mass should be less. it will be light in weight. Okay, so all of these dimensions you should look into. This first topic is completed, and the next session, inshallah, we will be covering and looking into the atomic structure and the bonding. I will upload today's lesson as well in Google Classroom. So all of you must join Google Classroom. Your weekly quizzes will be at they will be tomorrow. Yeah, tomorrow we will have a weekly quiz. So I will be giving you the first topic for as a reinforcement. Okay. Do we have any questions, any queries so far?
Miss, I didn't get where you will send the classroom code.
The classroom code. Have you texted me? Text me on my number, on my WhatsApp. I will add you to the group if you're not added. Okay, Ayla?
I don't think I have your number.
Okay, ask your parents.
Okay, I will.
All right. Okay. Anybody else? Have the rest of you joined the WhatsApp group?
Yes.
All right, then. Take care, Allah Hafiz. Thank you. This is it from my side today.
Hafiz.
Allah Hafiz. Bye-bye.